Hello, hello, hello. Welcome everybody. Hopefully you can all see me and hear me. Is that working? I can't see myself yet. Welcome to our A-level chemistry redox A-level chemistry Sunday session on redox reactions. So welcome. Hello everybody. Please feel free to say hello in the chat. It'd be nice to see who's here, who's waiting. Oh, that's exciting. Oh, hello Rowan. Nice to see you again. You're up for a bit more of a challenge. Hello Mariam as well. Hi Alex. And hello Love. That's nice to see you. Hi Zara. Hello Khadija. Lovely to see you guys. Oh, I'm not going to attempt to pronounce your name, but hello MXRI. You, that one. Hello, welcome. Hi everybody. Welcome if this is your first time. Hi Kyle as well. Hello. Welcome if this is your first time, and welcome back if you are a regular viewer or you've been to any of our previous YouTube sessions. This is an A-level chemistry YouTube video on redox reactions. So we're going to look at what redox reactions are and hopefully try some exam questions and just double check our knowledge. Hi Joy as well, hello. If you haven't already, please feel free to download today's slides. The link is in the description so that you can use them, you can save them for a later date, you can use them for revision, you can use them now, you can fill them in now along with us. That's a very useful revision technique. It's good for you to save them as well, and then you can redo them again at a later date, just double check your knowledge, redo the exam questions, all this sort of thing. So really useful content, a useful revision technique. Hello Saifal as well. Apologies if I've said your name wrong. And Mariam, you said, will this cover the AQA specification? Yep, we look at AQA, EdXL and OCR. And if there's any major discrepancies, I will point it out between the different exam boards. But otherwise, they are all very similar in a lot of the main content that they expect from you. Hi, Emily, as well. Hopefully everyone's doing well. Everyone's ready to have a go at some redox reactions and look at what redox is and get our head around the main concepts. Apologies, I'm not sure what you're asking there, I'm afraid. But hello, hi, well done, hi, lovely. Right, I think we should get started because I always talk too much and then we run out of time. So let's have a look then. So welcome, this is our A-level chemistry, Sacrifice A-level chemistry YouTube class on redox reactions. Okay, so a little bit about me. I'm Alyssa. I am one of the tutors here at SnapRevise. I'm the lead GCSE chemistry teacher, but also love A-level chemistry. I actually love all the sciences, but chemistry is my fave. I've got a PGCE in chemistry education and teaching science with chemistry as my specialism, and I've been teaching and tutoring for the last 6 years, or over the last 6 years actually now. Today for our A-level classes, we have got a free trial. So if you are interested in trying our tutoring, I will show you a little bit at the end about what we offer. We'll have a quick look at the website as well. But if you are interested, please feel free to enter the code RR7 at the checkout, and you can get 1 week free. You can see what it's like. You can come along to our classes, see if it feels like the kind of thing you'd be interested in. So just follow the steps on the slide in front of us, to access that free trial. And it's only available for 24 hours. So if you're interested, please feel free to use that, but it will expire in 24 hours time. The code has been put in the chat as well. Hello. Again, apologies if I pronounce your name wrong. Mushafi. So apologies if I've said your name wrong. It's very difficult when I can't hear you guys repeating it back to me, but I'll give it my best shot. Okay, so what we're going to look at today then. So today in this session, we're going to hopefully understand the rules for determining oxidation states. Key, if you want to do anything with redox, is to be sure on your oxidation states, on determining oxidation states. We're going to then use oxidation states to identify redox reactions and the parts of redox reactions, what the different species are in a redox reaction, what they do, and we're also going to look at half equations, another challenging part of chemistry, but one that is really useful and that you need to use in a couple of different topics actually, so very useful skills. What we're not going to look at in this session is disproportionation, and if you're not sure what that is, that's fine, but we're not going to look at that specifically in this class, although I may mention it if it comes up. Hello. Hi, Joel. Hello. Lovely. Right. Okay. So just to answer your question, Mariam, as well, these are the specification points from AQA that we are going to be covering in this session. So please feel free to have a read through on your slides and just double check that you're happy. And if there's anything you're not happy with, or we come across a question and you think, oh, that doesn't quite fit with what I read, come back to me and we can talk through it together. That's absolutely fine. This is OCR. So these are specification points that we're going to be covering from the OCR spec. And these are the specification points from Edexcel. So it does look different. Some of the specifications are a little bit more descriptive than others, but it's all covering the same content. It's just the way that they describe them. But the specifications are really, really useful revision tools. So if you haven't gotten used to yours, navigating through it, reading it, understanding what they want from you, it's a really, really useful revision tool. So I really highly recommend you have a look at it. So let's go through what we already know. So some of this you might have known from GCSE, some of it you might just know from your classes. What is an ion? How do we define an ion? And we do try to be very specific about using terms when they are correct to be used, when we should use them. So what is an ion? How would you define or describe an ion then? How would you describe or define an ion? What is an ion? Lovely. Good. So we've got a couple of different definitions here. Some we need to be a little bit careful because an ion could be an atom, a single atom, or a group of atoms. So you could say an atom or group of atoms which has lost or gained electrons to become charged. That would be fine. You could also say a particle because that would cover an atom or group of atoms as well. That would be absolutely fine. So brilliant. Looks like everyone has got this correct. So it's a ion is a group, or actually let's say an atom or group of atoms that has lost or gained electrons. So I'm going to be really lazy and just write E- because that's what we use when we write half equations. Lost or gained electrons to become charged. And you're right, it can be either positive or negative. Please let me know if you can't read any of my handwriting, because I can read it out to you again, or I can try and rewrite it. But otherwise, it looks pretty good, guys. Yep. Lovely. A particle that has an uneven number of protons and electrons. Yep, that would work as well. Lovely. Okay, what about reduction and oxidation? What are the definitions, or how do we determine the difference between reduction and oxidation? And I'm thinking, because at A level we nearly always, not always, but nearly always focus just on electrons. What's reduction and oxidation in terms of electrons? What's the difference between them? Nice. Wow. Okay. Jono, I like that because you've covered everything basically, which is fabulous. It looks, yeah, good. It looks like everybody's that I've read have got it correct. Fabulous. So reduction, if you know the kind of acronym, oops, well, not even acronym, is it? Oil rig. Oh, why have I put an M? What is? I wrote an A and then an M. Don't know what's going on. Oil rig. So oxidation is loss, reduction is gain of electrons. So brilliant. So reduction is gain of electrons. Oxidation is loss of electrons. And you're exactly right. We could talk about it in terms of gain or loss of oxygen as well. So oxidation being the gain of oxygen. And we can also talk about it in terms of oxidation number or oxidation states, but we're going to do that a bit later on, so I won't write that down. Fabulous. If anybody at any point has any questions, please pop it in the chat and I will do my best to find it. If I ignore you, it's not on purpose. Just send it again. I will try to respond to everything that I see. So please just send your question again. Oh, I love that. I've never seen that, Leo the Lion. So LO, loss is oxidation, and GR, reduction is gaining is reduction. I like that. That's very nice. I've not seen that one before. Cool. Everyone learned something. So what about reducing agents and oxidizing agents? What does a reducing agent do? What does an oxidizing agent do? And this is always, well, not always, but it's one of the things that students get stuck on, and totally understandably. A reducing agent, it does what? What does it do? Nice, Sarah. Good, lovely. Well done, Joel. Well done, John, as well. And Sarah, you brilliant. Yeah, brilliant, fantastic. Yep, Mariam, exactly. Lovely. Yep, well done, guys. Exactly. Okay, perfect. So reducing agents cause another species to be reduced, i.e. to gain electrons. I.e. gain electrons. And therefore, by reducing other species, they themselves are oxidized, they must lose electrons. Exactly right, which is what lots of you have said. Fantastic. And vice versa for oxidizing agents, they cause other species to be oxidized. They are an oxidizing agent. They are oxidizing something. And therefore, they themselves are reduced. Yeah, exactly. Nice, Rowan. Exactly right. Yeah, well done, everybody. Yeah, exactly. Brilliant. Fantastic. Well done, guys. Lovely. Okay, so now we're solid on those, hopefully. Let's have a look at oxidation states. What do we remember? What are the rules for oxidation states when we're looking at compounds? Or I shouldn't actually maybe say, yeah, in compounds. What are our rules? These are in compounds, by the way. What are our rules for oxidation states? So when you're looking at like an element, for example, or when you're looking at a molecule, or when you're looking at an ion, or whatever, what rules do we go by in order to determine oxidation states? Anybody know? Lovely, Rowan. That's really nice. The sum of all charges must equal the formal charge of a particle. Brilliant. Exactly right. So ions have an oxidation state, and the sum of all of the oxidation states within that ion must add up to the formal oxidation state. That's nice. That's good. I like that. Elements, pure elements are always 0 as well. Brilliant. Nice, Sarah. Exactly right. Good. Yep, we'll come to those in a second. That's good as well. And the final one, which I'm not sure we've seen yet, is that uncharged compounds always add up to 0. So individual elements inside them may have oxidation states, but together they add up to an overall oxidation state of 0. Good, let's write that in then. So we've got pure elements, for example, O2, Cl2, etc. Always equal 0. We've got ions have an oxidation state equal to their charge. Actually, I'm not sure we did mention this one, did we? So if sodium ion has a charge of +1, that's also its oxidation state. It's +1. E.g. O2 minus has an oxidation state of 2. Oh, what has gone on there? No, my pen. There we go. O2 minus has an oxidation state of -2. Shalaj, hello Shalaj. I do remember you. How are you doing? Sorry, I've totally lost track of thought there. And then uncharged, or we could say charged there. So uncharged compounds add up to overall charge. So in an uncharged compound, they add up to 0. In a charged compound, that add up to whatever the overall charge is. Enjoying the summer. Good. Yes, Rowan, that's really interesting. That's a very good point, actually. Yeah, it's because actually a lot of the time our things are in a bond within a bond, or so like maybe a covalent bond or a metallic bond or whatever, and therefore we can't necessarily say that the electron has actually been lost or not, because they're all still part of the compound. So that's a really interesting point. Yeah, very good. Okay, so hopefully we're all happy with these oxidation numbers as well. So as I think it was Zara said, oxygen is nearly always 2-. So that's one of the first things that we can fill in, is oxygen is nearly always 2-, apart from in peroxide, H2O2, in which case it's -1. Basically everywhere else that you're going to see it, oxygen will be -2. They may decide to introduce it to you when it's bonded to fluorine, highly unlikely, but because fluorine is much more electronegative than oxygen, it definitely steals the electrons, and therefore oxygen won't have its electrons. It'll lose its electrons. So in that case, it will be +2. But it's very unlikely that they'll introduce that to you. So nearly always oxygen can be -2. Hydrogen, again, is a group 1 element, or we consider it to be a group 1 element. Therefore, it forms a +1 charge. Fluorine, chlorine, bromine, iodine, etc. are all -1s. Again, like I said, our group 1s are +1s, our group 2s are +2. Aluminium is in group 3, and it's a metal, so it forms +3, etc., etc. So hopefully these are all rules that you guys are all happy with. Let's have a go at putting them into action. So, calculating oxidation numbers. I want to know the oxidation numbers of all 3 elements in H2SO4. Mariam. Sorry, apologies if I've said your name wrong there. What's the best way to memorize exceptions? There are very few exceptions. So I would write them maybe on individual flashcards and just test yourself on them. There are very few exceptions. Oxygen in hydrogen peroxide is one of them, and hydrogen in hydrides is the other. Those are the 2 most common exceptions. Then there's oxygen in with fluorine. Otherwise, everything follows pretty much the rigid rules. So I would, flashcard and just keep copy, cover, repeat kind of a thing, or like what's the oxidation state of this in? Test yourself. Yes, I was right. That sort of thing. Lovely. Really good, guys. Fabulous. It looks like you guys are doing brilliantly. So what can we, what do we know already? Well, we know that oxygen, because it's not bonded to fluorine, or well, it's not in H2O2 either, so oxygen must be -2. Fabulous. Hydrogen, again, this is a normal compound, a regular compound. It's not a hydride or anything, so hydrogen is going to be +1, so those are nice and easy. And then exactly as you guys have done, we know the overall charge has to be 0. If the overall charge is 0, and we've got 2 lots of +1, and we've got 4 lots of -2, our total positive charge there is 2. Our total negative charge there is -8. So what has to fill the gap so that the total is 0? 2 plus something -8 equals 0. So S must be +6. Really good. Well done. Fabulous. Good, good, good. Nice one, everybody. What about S8? Oh, Rowan's already given it a go. Fabulous. What about S8? How do we know what's the oxidation state of sulfur in S8? It is algebraic. Yeah. It is. It's a puzzle. I love solving puzzles, and I find doing oxidation states like a puzzle, which is quite fun. Good. It's 0 because it's an element. This is how we find sulfur in its elemental form, or one of the ways, I think. The main way, anyway, that we find sulfur. So the oxidation state must be 0. Lovely. Really good, guys. What about this one then? What about chlorine and oxygen in ClO3 minus? ClO3 minus. What are our oxidation states of oxygen and chlorine in this ion? Nice, lovely. Okay, just double check. So we know that our overall charge is -1 because it's got the little minus sign here. Oxygen is not an exception, exactly right. So we've got a charge of -2 on each oxygen, which means the total charge from the oxygen is 3 lots of -2, which is -6. But the overall charge has got to be -1. Just check your maths. The whole charge has got to be -1. So we want to work out what our chlorine is. So something -6 has got to equal -1. Something -6 has got to equal -1. So 5. Why have I got 7 written down in my answers? Apologies. I hadn't even done the maths myself. I've got 7 written down in my answers and it's wrong. It's got to be +5. +5 -6 equals -1. I must have the wrong answers written down. Whoops. Whoops the daisies. Good. Well done, guys. I'm glad you guys are on the ball. You've got it. Good. So +5, because +5 -6 equals -1. Well done. Good. What about our potassium permanganate then? Our KMNO4. Ah, lovely. Good. What is it? So, again, our oxygen is a good place to start because it's not in a weird one. It's not one of the exceptions. So oxygen has got to be -2. We know then we've got 4 lots of -2s. Potassium is a group 1 element. Group 1 elements have a charge of +1, so they have an oxidation state of +1 as well. Really good. Well done, guys. Looks like you guys are getting it perfect. Fabulous. So the only one that we're unsure about, therefore, is the manganese. Well, overall, we must have a charge of 0 because it's a neutral compound. So +1 plus something -8, which is our 4 lots of -2, has got to equal 0. So what's the missing number? Well, it's got to be +7. Good. Good question, Jonelle, because oxygen is one of those solid elements. That's why we give you the exceptions for oxygen and not for other things, because a lot of other elements can vary their oxidation states. That's a really good question, though. Really, really good question. Because oxygen is more securely found, because it's more electronegative, ever so slightly more electronegative, it's more likely to keep its oxidation state as -2. We do give you the exceptions because they like to put the exceptions in just to be annoying. So although we talk about oxygen as having exceptions and we don't really talk about other things as having exceptions, there are lots of elements that have other exceptions. Maybe I should mention that next time. So really good question. It's because I am much more sure of the oxidation state of oxygen than I am of chlorine in this case. Therefore, we'll do oxygen first and then solve for chlorine. Hopefully that makes sense. It's a great shout, though. Maybe we should mention that next time. Anybody not happy, or anybody got any questions? Any other questions about any of those? Yeah, exactly. It's the ratio, or they believe, at least I don't know if they've confirmed it, that the electronegativity comes from the ratio between protons, neutrons, and electrons in atoms. And for fluorine, it's like almost perfect, meaning that the electronegativity, the effective nuclear charge of the nucleus is super, super high on attracting all of the electrons in from fluorine. Hence, it's got an incredible electronegativity compared to other elements. Yeah, brill, fabulous, thank you. Well done for pointing that out though, very good. Okay, let's keep going. So, redox oxidation states. We can calculate oxidation numbers of elements in reactants and products of reactions, and then we can determine if it has changed its oxidation state. So again, this is where our rules come in. We need to be more sure, or we can be more sure of some elements than others, and then some of them are going to change. So we hopefully know our transition metals love to change their oxidation states, so they will be one of the last ones that we calculate because they're likely to change their oxidation states. And then things like oxygen, for example, again, we know we can be much more sure of it, so we will do that one first. When the oxidation number goes up, is this oxidation or reduction? When the oxidation number goes up, is this oxidation or reduction? Yeah, good, well done. It is oxidation. Oxidation, the increase of an oxidation number is oxidation. When the oxidation number goes up, the element has been oxidized. Lovely. And therefore, hello, no worries, welcome, welcome. Lovely to have you here. When the oxidation number goes down, then hopefully we recognize that is the opposite, so that means the element has been reduced. So I always work out what oxidation means, and then the opposite's got to be reduced. And it makes sense. If you increase an oxidation number, it's getting more oxidized. That kind of, to me, it makes sense. So we can use that to help us remember which way around it is. Lovely. Yeah, no, whoops, never mind. No worries. Okay, so let's work out what's happened here then. Again, I'm going to draw a line down the middle. Let's do our reactants and products. So reactants, what are the oxidation states of our elements in the reactants here? What are the oxidation states of elements in our reactants of this reaction? If there's any that you know for sure, start with those and then work out what the other ones will be. Actually, I'll just make that a little bit smaller. Nice, you've jumped straight in. Hi, Laura. I've only just seen you appear. Hello, hello, welcome. Nice to have you. Okay, good. So we can start with aluminium because it's an element on its own. Because it's on its own, we know it has to have an oxidation state of 0. Oxygen is not as a peroxide or anything, so it can be -2. That means our iron, therefore, has to be +3. Good, because we've got 3 lots of -2, which gives us a total of -6. There's 2 lots of something. The overall charge has got to be 0, so 2 lots of something have got to equal 0. So 2 lots of something -6 has got to equal 0. And so that something has to be +3. Brilliant. Yep, lovely, good, good. Looks like everyone's doing really well. What about for our products then? I think some of you have already gone ahead and done this, which is fabulous. What about our products? So this time, iron is the element. So iron has got an oxidation state of 0. Oxygen, again, is not a peroxide or anything like that. So we know it's got to be -2. And therefore, aluminium is going to have the charge. It's the same calculation, but I'm going to write it out anyway. So our aluminium has gone to be +3. Has changed. Good. So what are our change in oxidation states? Fabulous. Iron has gone from +3 to 0. So its oxidation number has reduced. So Fe was reduced. And aluminium has gone from 0 to +3. So aluminium was oxidized. Really good. Looks like lots of you have got that already, which is fabulous. Nice, well done. Pawan as well, that's good. Lovely. Loads of you getting that right. Okay, how is everyone feeling so far? We're doing pretty well, I think, in terms of time and stuff. So how are we feeling? Give me a 1 if you like. This is pretty straightforward. I'm quite happy with what we've done so far, or a smiley face. If this is okay, you might need to practice it a little bit. You think you're following, you're doing all right. Give me a 2 or a middling face. Or if actually not happy at all, don't understand any of it, really, really going to need to go over this again. Give me a 3 terrified face. Lovely. Oh, Mariam, good point. What do we say about oxygen? Yeah, so oxygen, if we were looking at writing redox reactions or half equations, we would disclude oxygen. It wouldn't appear because it hasn't changed. It's a spectator, as somebody, they've just appeared off my screen, but somebody just said it's a spectator. Great question. Does the A-level go into experimental design like a redox titration? I'm not 100% sure I know what your question is, Rowan. What I think you mean is if you do the redox, lots of the redox topics that you do at A-level do redox reactions, but they're I don't know what the word is, predetermined. It's already been decided which redox reactions each A-level will look at. So AQA, EdXL and OCR decide in their specification which ones they want the students to study. And so you look at them and just study those. There's no design about it, unfortunately. You just have to learn the couple that they've decided they'd like you to know about. Usually really handy ones, ones that are used often in industry, but we don't get to design any, unfortunately. Nice, fabulous. Okay, let's keep going then. So an exam question of what we've just been doing. So this question is about group 7 elements. Chlorine can be made by the redox reaction below. I'm not going to read it out. It's too long. Using oxidation numbers or oxidation states, show what has been oxidized and what has been reduced in this reaction. So using oxidation numbers, show what has been oxidized and what has been reduced. So we need to show some oxidation numbers and we need to state, basically, state what has been oxidized and what has been reduced. So feel free to jump straight in and have a go with the answers. Otherwise, let's write up some numbers. Now, feel free to write it on the side of your screen, somewhere else, on a piece of notepaper. What I'm going to do is, because I like using what they've given us, because it's really useful, I think, in an exam to be able to use what you've been given, I'm going to write all my oxidation numbers above the elements on my, what's it called? Equation, my chemical equation. So what do we already know? I'm going to do all of them because we don't know what has or hasn't been oxidized yet. So oxidation state of, or oxidation number of oxygen, it's in manganese, it's in a manganese oxide, so it's not a peroxide, so it's going to be -2. And there's 2 of them, so the total negative charge here is -4. The overall charge has got to be 0, so the positive charge from the manganese has got to be +4. Let's do, I might write it up here as well, just in case you can't see my writing. So oxygen is -2, so manganese has got to be +4. Hydrogen chloride, okay, a challenging one, but hopefully you guys recognize when you've been doing acids and alkalis that hydrogen and chlorine, hydrogen is +1, chlorine is -1. It's actually straightforward, but sometimes, we get a little bit confused. So hydrogen is +1, chlorine is -1. +1, and that's just a nice straightforward 1-to-1 ratio, so we don't need to worry about any of that. That one's nice and easy. So hydrogen +1, chlorine -1. Then manganese chloride. So here, again, manganese is our transition metal. So that's the one that's going to be more variable. So I'm going to start with chlorine. I'm going to assume, therefore, that chlorine as a halide is going to be -1, and there's 2 of them. So the total negative charge is going to be -2, which means my manganese needs to be +2. It looks like loads of you have got this already, which is brilliant. So in my product, let's move that out of the way. In my product, my manganese has gone to +2. If anybody spots me making a mistake, by the way, please shout, because I do sometimes make mistakes. And I'm doing this in real time, so I will check my answers later, but I do these in real time. So let me know if I make a mistake. So chlorine's -1 as well. It doesn't change. It's not been forced to for any reason. So that's fine. Hydrogen and oxygen, again, they're not being forced to change oxidation states. They're quite happily in -2 and +1 oxidation states. Good question. Will this be posted in the channel? Yeah, it should be saved to our channel, so you can rewatch it at a later date and again, and you can download the slides and redo it again. That will be absolutely fine and a very good idea. So, and chlorine, I forgot, whoops, in an element there is also 0. So our oxidation number of chlorine has changed to, well, it's not changed, and it has changed to 0. Oh, thank you, Rowan. Yep, I just got there. I hadn't got to the end of my equation yet, so good spot. Well done. No, it's -1 in manganese chloride, but it is, you're right, 0 in Cl2. No, very good spot. Let's put that in there, MnCl2 in Cl2. So chlorine actually has 2 oxidation states in the products, or the 2 different species, 2 different parts, 2 different products involving chlorine have different oxidation. The chlorine has a different oxidation state in each of them. Yeah, exactly. It's twice in the products. Yeah, that's a complicated thing to say, that is. Lovely. So what's happened then? What has been oxidized? What has been reduced? Well, manganese has changed oxidation state. It's gone from +4 to +2. And if so, therefore, its oxidation state has reduced. So that is reduction. And what else? Our chlorine has gone from -1 to 0. So it's actually increased. So our chlorine has been oxidized. For chlorine, wouldn't you say it's just -1 to 0 doesn't add anything? Well, it does here, because that is the only thing that has been oxidized. And actually, maybe I should draw an arrow to there. The only thing that has changed oxidation state and increased in oxidation state is the chlorine in the Cl2. So because it's an element, it's in the elemental state of Cl2, it has got an overall oxidation state of 0. So we have to say that its oxidation state is 0. So it's important to note, if that makes sense. And that is, in this case, the only thing that's been oxidized. So it's the only thing we need, it's the thing we need to talk about, basically. So oxidized is therefore our chlorine. It's gone from -1 in HCl to 0 in Cl2. Actually, I put oxidation state. So its oxidation state changes from -1 in HCl to 0 in Cl2. What did I read? So reduction, what was reduced? The manganese. So its oxidation state changes from, and I'm stating what the oxidation states are of these elements in each compound that I'm using, because it's asked us to use oxidation numbers to show. So I have to include them in my answer, otherwise I don't get the marks. So the oxidation state changes from +4 in MnO2 to +2 in MnCl2. Good question. If there is a change with an element, for example, and there are 2 different oxidation numbers, would you note the biggest difference? Really good question, Miriam. I said I wouldn't necessarily mention it, but one of the things that you do look at is a disproportionation reaction. And in that case, the same element is both oxidized and reduced in the product. Here it stays the same, so it's not a disproportionation reaction, but it is an odd reaction because two different things happen to the same element. But yeah, if the question is asking you what is being oxidized and the same element is being oxidized but to two different extents, so maybe you've got iron that's being oxidized to +2 and +3 in the same reaction, then and it's asked you to say what has been oxidized, then I would mention both. In this case, it's asked what is oxidized and what is reduced. So we've mentioned the only thing that's been oxidized and we've mentioned the only thing that's been reduced. Does that make sense? So it kind of depends what the question's asking. It should be fairly straightforward in terms of the question, in terms of understanding what it is you need to say. So hopefully, if you come across a question like that's a bit odd, you will be led down the right path. How are we doing for time? Okay, not too bad. Anybody got any other questions? Really good questions, by the way, guys. Very good. So here marks are for 1 for each, and you need to have included the oxidation numbers to get the marks. Awesome, lovely, well done. Okay, let's keep going then. So one thing that we need to look at now is redox half equations. So half equations, hopefully you've met them before. If you haven't, a half equation is kind of what it says on the tin. It's half of the equation. The trouble is it's not always exactly half, but what it's talking about is it's talking about kind of half of the reaction, what's happening in part of the reaction. And when we talk about half equations, we are nearly always talking about a redox reaction. Reduction, the RED is reduction, and redox, the ox is oxidation. So one half is reduction, the other half is oxidation. And when we talk about half equations, we need to include electrons. It's kind of the key, I think, to a half equation is it's talking about what happens to the electrons in a reaction, the bits that we can't see or the bits that we can't really keep track of very easily. And it helps us as chemists to work out molar ratios in terms of knowing exactly how many reactants you might need to add together, or how much product you've produced, or maybe how much reaction has actually occurred, or when you're looking at anything to do with cells, batteries, circuits, you might use half equations to work out the exchange of electrons, the number of electrons that have been exchanged, etc. So really, really key part of chemistry, half equations. Yeah, exactly right. So yeah, electrochemistry. It's good, nice application in electrochemistry. Yeah, exactly. Okay, so how do we do these? Now, you may be given two half equations and asked to write the full equation. You may also be given the full equation and asked to write the half equations. Now, some people find one easier than the other. I think it often just depends on how your brain works, how you like to approach them. But if we're combining half equations to make a full equation, there's two steps that we need to do. One, we need to make sure that we've got a balance of electrons. So in the same way that when we're balancing an equation, we have to have the same number of atoms of each element. We can't just randomly pick up a chlorine atom out of nowhere that ends up in the product. It has to have come from somewhere in the reactants. And it's the same with electrons. We can't just randomly pick up an electron that we need to put it in the product. It has to have come from somewhere in the reactant. So we must make sure that there is a balance of electrons being exchanged. We also don't want to have random electrons just hanging around. They're going to need to go somewhere. So first things first, we need to change my color. First things first, we need to balance, can't spell, still can't spell. Balance the number of electrons that are being exchanged. Balance the number of electrons that are being exchanged. Good, yeah, fabulous. We have to keep the electron count equal. So we balance the number of electrons being exchanged so that we know the number of electrons being given up is the same as the number of electrons being gained, and then we remove the electrons. That way we know, hopefully, we will have a balance of charge and a balance of mass in our overall equation. So then we remove the electrons. Oops, can't spell. I still can't spell. Electrons, and combine the half equations. So in this case, we've got two half equations. We've got iron going from Fe3 plus to Fe2 plus, and we've got tin going from solid to Sn1 plus. Now here, the iron picks up one electron and the tin donates one electron. So that's nice and easy. They're already balanced. We know that every electron that's given up by iron is picked up by tin. So we know it's a 1-to-1 ratio of those two reactions. So we can just remove the electrons and combine them. Now you can write it out in full and then remove the electrons and then write it out properly. That's fine. I'm going to skip that step just for ease of time and remove the electrons straight away. So I'm writing all of the reactants together. So that means all of these, but without the electrons, on one side of my arrow. And then I'm going to write all the products, but without the electrons on the left. So that means my iron, Fe3 plus, aqueous, plus, get rid of the electron, tin, Sn, products goes to make my products, and again, without the electrons. So Fe2 plus, oops, I didn't write in my state symbol, aqueous, plus Sn, oh, not even solid, Sn plus aqueous. If anybody's not happy with that, please let me know. So what I've done is I've combined all of the reactants from both half equations, removed the electrons, and then combined all the products from both half equations and removed the electrons. And that then, therefore, is my full equation. Fe3 plus Sn makes Fe2 plus Sn plus. And if I just double check, I should, as long as I've counted all my electrons correctly, and I've balanced my electrons, I should have the same charge on both sides of the equation. So I've got an overall charge of 3 plus on the left, and I've got an overall charge of 3 plus on the right in my products. So I know that I've done that properly. I've also got the same number of atoms or species particles of iron and tin on both sides of the equation. Perfect. Let's try something a little bit harder then. Here I've got Fe2 plus goes to make Fe3 plus and 1 electron, and MnO4 minus plus 8 H pluses plus 5 electrons makes Mn2 plus and 4 waters. So what do I need to do in order to make sure that I've balanced the number of electrons that have been exchanged? What do I need to do here? How can I make these balanced? How can I make these two equations balanced? Nice, well done, Rowan, exactly. We're going to multiply the iron equation by 5. We need to make sure we've got 5 electrons so that we're exchanging 5 electrons in both places. So that means we're going to need 5 iron 2 pluses, which are going to make 5 iron 3 pluses and release 5 electrons. Yeah, exactly, well done. Good. Fabulous. Okay, so then we can combine the two and remove our electrons. So 5 Fe2 plus aqueous plus MnO4 minus aqueous plus 8H plus aqueous. I'm removing the electrons. I'm not interested in the electrons. Goes to make all my product 5 Fe3 plus. I'm removing electrons, so I don't care about that. Plus Mn2 plus aqueous plus 4H2O. And again, if I just double check, it should be a balanced equation. I should have the same number of elements of each, or particles of each, which I do, and I should have the same overall charge on both sides. So 10 plus 8, 18 minus 1, so 17, a total charge of 17 on the left, and 15, 16, 17, a total charge of 17 on the right. Perfect. So that is my full equation. Yeah, good, lovely. Well done, guys. Okay, I've just realized the time, so I'm going to need to speed up. Okay, Okay, so we can use half equations. Sorry, we can use oxidation states to infer half equations from full equations. So that means we can work out what a half equation is going to be from the oxidation states and from a full equation. So let's work it out. I'm going to speed through working out the oxidation states just to save time. So if you want to, please let me know what the oxidation states are of all of these elements, and then we can work out what has happened to each element, if anything. And therefore we can write our half equations. So what's happened to the copper, what's happened to the oxygen, what's happened to the nitrogen, what's happened to the hydrogen, and therefore can you write our half equations to show what has happened. It's the same thing we were doing earlier when we're looking at what's been oxidized and what's been reduced. This time we're just writing an equation to show what's been oxidized and what's been reduced. So in copper oxide, oxygen has -2, which means copper must have +2. In NH3, hydrogen is going to have +3, and +1, and there's 3 of them. So nitrogen is going to have -3. Lovely, it's looking good. And then the other one, copper here is an element, so it's elemental 0. Oxygen is not in a hydride or anything, so it's still -2. And then N2 is elemental, so that's going to be 0. And our hydrogen is +1. So what has changed? Well, our copper has gone from +2 to 0, so that has been reduced. I think I've changed my colours over now. That's awkward, isn't it? Whoops, sorry guys. And then my nitrogen has been oxidized. So let's write those equations. I'm just going to try and get to the end of the slide, and then we might have to skip the exam questions. Too much to do. Right, so let's write an equation. So copper has gone from Cu2+ to Cu0. So how's it, sort of Cu normal. So how's it done that? Well, hopefully I can see that I must have gained 2 electrons to become a copper atom, to become a neutral copper atom. My copper ion must have gained 2 electrons to become a copper atom, and I know that this is reduction anyway. The gaining of electrons is reduction. And similarly, my nitrogen has gone from N3- to N2. And because it's N2 in my overall equation, I'm going to need to have 2 lots of N3-. And that means it's gained a total of 6 electrons. Oh, no, it hasn't. What am I about? It's not gained a total of 6 electrons. It's lost a total of 6 electrons. Hence, it's been oxidized. And so those are my 2 half equations for this overall reaction. Oh, thank you. Thank you for telling me my colours are correct. I thought I'd swap them over. Brilliant. Okay. Anybody not happy with that? What I'm going to do is I'm going to write, actually, just because then we might even have a go at doing maybe one exam question. I'm just going to write the correct equations on the bottom. Oh no, okay, let's do it together. Let's do it together. We'll just do that one. So again, speeding through because there's always too much to do. Speeding through, working out which each of these are. Oh, there's 2 here. Oh, I've written them in different orders. No idea why. Let's write them in the same order. So manganese here. Oh, we did this one before, didn't we? Does it matter which side you write the electrons on? Good question, Zara. Yes, it does. If it's reduction, they have to be gained. So something has to be gaining them to produce something else. If it's reduction, the copper has gained 2 electrons to become a copper atom. In our oxidation, our nitrogen has lost 3 electrons. So it started off as a whole N3-, and then it lost 3 electrons, or 2 of them both lost 3 electrons. So both of them together lost 6 electrons. So they started off as one unit, and then it produced N2, and 6 electrons. So it does matter. It tells us what happened to the electrons, basically. So it does matter. Great question, but it does matter. Lovely. Thank you for doing that, Rowan. I'm just going to write it in. So Mn4 plus, that's O2H plus 1, chlorine minus 1. And then we went to manganese plus 2, 2 minus, or 1 minus, minus 2 even. I don't know what I'm saying. Plus 1. And then chlorine is minus 1 and 0. Again. So if we're going to write our half equations for this, we know that our manganese has been reduced and our chlorine has been, in one case, oxidized. So we should be able to write a half equation that shows exactly what's happened with the electrons. So manganese has gone from Mn4 plus, or plus 4, Mn4 plus, and it has gained 2 electrons to make Mn2 plus, and our chlorine has gone from Cl minus 1 to Cl2, and again, because it's a Cl2, it needs 2 of them, and that means it must have lost 2 electrons. So it's been oxidized. Nice, very good. Yep, exactly right. Well done, Rowan. Okay, how are we doing for time? Okay, I need to speed on. Right, hopefully everyone is feeling at least all right about that. It does need a lot of practice. I won't give you all the answers for this because I think it would take too long, but please feel free to have a go at those and just double check. These are all old exam questions, so you may even be able to find the answers to these on the internet if you have a quick Google. Hopefully, we've now looked at understanding the rules for determining oxidation states. You're happy with using oxidation states to identify redox reactions and understanding the use of half equations. So just to finish off, just to let you know, we've got lots of upcoming web classes, so please feel free to go and have a look at that. There's the YouTube schedule it hopefully will appear in the chat in a second, so if you want to have a look at our schedule. Otherwise, just have a look on the YouTube channel for our schedule. We do offer, and it's currently going on at the moment, some A-level chemistry tutoring. Now, when term starts back up again, we have 4+ classes a week. That includes tutoring and drop-ins. So I'll explain what those are in 2 seconds. We cover the full curriculum. We have these amazing handouts that you can download, take home, use for revision, practice your exam questions, etc. You can look back on the past recordings, so you can rewatch classes, or if you miss a class, you can watch it to catch up. And we get the one-on-one support as well. So if you want to try this out, at the moment we're on our summer class schedule, but if you'd like to try it out, there's 1 week free trial. So if you use the code RR7 when you check out, you can get some 1 week free trial to see if the classes are what you would like. And I'm just going to show you now what we've got on our website. So if I just stop sharing that. Oops, I pressed the wrong button. Oh no, this is where my laptop freezes when I don't want it to freeze. There we go. So if I just share this screen with you. So this is our website. So if you're an A-level student and you'd love to look at our amazing revision cards, please feel free to have a look at those, because we have all of the content that you need. I mean, this says biology, but we've got chemistry as well, and physics, and I think maths. But if you'd like to have a look at those, please feel free to have a look at those. They are really, really good. It's concise. They cover the whole specification, and there's worked exam questions on the back of each card. So it's amazing revision resource there. But if you're interested in tutoring, if you go on the tutoring website, click on chemistry and scroll right down to the bottom, you can see an example of some example classes. They're very similar to our YouTube classes. You can see the schedule, so you can look at what's coming up and plan whether or not you want to join us. At the moment, we just have web classes, but we also offer, when term starts again, we offer drop-in sessions. And again, you can see an example of this, where we spend the whole hour going through exam questions. So that's interesting to you, or something that could be useful, please feel free to have a look at our schedule. Drop us an email at hello@snaprevise.co.uk if you have any questions about it. But if you'd like, I think, well, if you look at any what's the word? Any document, no, I don't know what phrase I'm looking for. Research, that's the phrase I'm looking for. If you look at any research, you'll see that practicing exam questions is a massive, massive help when it comes to revision. And so we have classes that are dedicated to just practicing exam questions. You can request them, or you can just turn up and have a go at whatever topics have been requested by other students. And we talk through them at your pace. We answer all your questions. It's a really, really good revision resource. So please feel free to have a look at those. Pop over onto the SnapRevise website, snaprevise.co.uk. We've popped a link in the chat, and drop an email if you have any questions. Unless there's anything that anybody has urgently, or any questions I've missed and you'd like to send again, please feel free to drop them in the chat. Otherwise, I'm going to disappear. But I hope you have a lovely, lovely rest of your weekend, and enjoy your summer holidays. And I'll see you for our next session at some point soon. Thank you so much for being so positive and engaging. It's brilliant. Really good. Lovely to have you. So thank you so much. Oh, well, I'm so glad. And thank you so much, everybody who has popped some amazing, lovely comments in the chat. It's really nice. Thank you very much, guys. Okay, have a lovely rest of your summer holidays, and I will see you soon. Bye, guys. Thank you very much.